The last of our background lectures is designed to give you a framework of understanding with regard to geologic time and geologic dating. In part one, we will focus on relative dating. Having a time scale is important to our understanding of Earth history. Rocks record geologic and evolutionary changes throughout Earth's history. Without a time perspective, these events have very little meaning for us. There are two ways geologists determine geologic time. Numerical dates specify the number of years that have passed since an event occurred. For example, the limestone is 250 million years old. Relative dates place rocks in a sequence of formation. For example, the Hermit Shale is older than the Coconino Sandstone. We are going to begin with relative dating because that is how the geologic timescale was initially determined. First, we have to understand the principles of relative dating. The first three apply primarily to sedimentary rocks, with the exception of lava flows and ash beds, and are called Steno's laws. The principle of superposition states that in an undeformed sequence of sedimentary rocks, each bed is older than the one above and younger than the one below. This principle also applies to surface features like lava flows and ash beds. In essence, the beds on the bottom are older than the beds on the top if the beds are all still horizontal. This is a photo where the principle of superposition applies, with oldest beds on the bottom and youngest on the top. Second is the principle of original horizontality, which states that layers of sediment are generally deposited in a horizontal position, and rock layers that are flat have not been disturbed by tectonic forces. Third is the principle of lateral continuity. It states that beds originate as continuous layers that extend in all directions until they eventually thin out or grade into a different sediment type. This is a photo of sedimentary beds that have been acted upon by tectonic forces causing tilting. We know from original horizontality that they were originally deposited in horizontal strata. These beds were originally horizontal sedimentary beds, but they have been folded by tectonic forces. At the time of deposition in the top diagram, all of the sediment extends out in a sheet in all directions. As erosion removed some of the sediment, you end up with a canyon or a river valley, as in the bottom diagram. You can assume that the horizontal beds on each side of this canyon once existed where the rock has removed sediment because of lateral continuity. The Grand Canyon is an excellent example of lateral continuity. The Redwall limestone and the Coconino sandstone are found on both the north rim and the south rim of the canyon, so we can infer that they existed in the center at one time because of this principle. The next two principles are not just applicable to sedimentary rocks. The principle of cross-cutting relationships states that younger geologic features will cut across older geologic features. This can apply to any rock type or geologic feature, such as a fault. Inclusions are fragments of one rock unit that are enclosed within another rock unit. The principle of inclusions says simply that the rock containing the inclusion is younger than the inclusion itself. In this photo, several igneous intrusions called dikes are cutting across another igneous rock. This means that the dike is younger than the rock it cuts across. In this photo, the white line is tracing a fault through volcanic ash beds. By the principle of cross-cutting relationships, this means the fault is younger, since it cuts through all of the exposed beds that had to have been there first. Take a moment to look at this photo, and using the principle of cross-cutting relationships, determine the order of these features in order from oldest to youngest. If you said B, A, D, and C, you are correct. Xenoliths are inclusions in an igneous intrusion that form when pieces of surrounding rock are incorporated into magma but do not melt. There are inclusions in the purple sedimentary layer that indicate the sediments were deposited on top of the weathered igneous mass. So in this illustration, the green xenoliths are older than the orange igneous intrusion, and the orange igneous inclusions are older than the purple sedimentary rock. In this photo, you can see a xenolith of green peridotite in a black basalt. So, from what you know now, which one is older? If you said the xenolith is older, you are correct. We have reached the end of part 1. In part 2, we will continue with relative dating.